Hey guys, so we took a small detour to understand certain aspects of DFT calculations. Now we will get back on our OS and proceed in understanding tensor analysis. Now if you could recollect, of course it's been a while, but if you could recollect, the reason we introduced tensor, or the context in which we introduced tensor, is when we want to understand the mechanical behavior of materials, particularly in the atomistic scale. Now, when you consider metals or any crystalline materials for that matter, the atoms are regularly arranged. So that is a characteristic feature of crystalline materials. They have a long range regular arrangement of the atoms. And the resistance offered by these atoms when you impose a mechanical load to a crystalline materials, it generally depends on the plane that you are considering and the direction you are focusing on. So now you have an entity, and to describe this entity, you not only need the direction, like in case of velocity, but you need both the plane. You need to describe both plane and the direction. So that is where we introduce the concept of tensor, and the etymology of tensor, it stems from understanding what happens to a material when you impose a tensile load or a stretching load. So that's the reason we call it as a tensor. So when there are other mathematical concepts that some from other physical studies, we have one mathematical concept that stems from the material's behavior. So of course we are proud of it. Now I guess I mentioned this earlier, but nonetheless it's worth mentioning again. Now if I consider this tensor, what it allows me to do is allows me to express the behavior of material in a more comprehensive manner. It allows me to focus on a specific plane. It allows me to focus on a specific direction in that plane. We also saw that despite its comprehensive nature, the tensor representation is implicitly bound or coupled with the frames of reference. So what I mean by that is, let us consider for an example two grains. A system, a bicrystalline system, meaning there are two grains associated with this system. So we have a continuum and there are two grains associated with it. So what we mean by grains is, in each of these grains, the atoms are oriented in their specific characteristic way. So in this case, the atoms are oriented in this direction. In this case, the atoms are oriented in this direction. Now, if I want to introduce a frame of reference for this grain, it will be of this sort, at one direction along the orientation of the arrangement of atoms, another direction perpendicular to it. So let us call this as I and G. On the other hand, if I want to describe or introduce a frame of reference for this grain here, this frame of reference will be of this form. Let's call it as L, and another axis, let's call it as M, one along the orientation of my atomic arrangement, and one other axis that is perpendicular to the orientation of my atoms in this frame. Now if I want to describe, let's say, the strain experienced by a specific plane of this grain in a specific direction, I would express it as epsilon ij. So I have a bicrystalline system, a system that comprises of two crystals. I impose an external, let's say, a stretching load to it. So let us assume that this is my bicrystalline material. I hope you are able to see it, and I'm trying to stretch it. So this has two grains in them, and the response offered by this material depends on the orientation of the atoms. So if I want to describe the response offered by the material in grain 1, so I will be using this notation. It involves I and J, so the corresponding axes are here. And in this case, the strain offered by this atom, the grain 2, I represent it as epsilon L and M. Now, of course, these are tensor representation of the response offered by the material, that is strain. It is expressed in the tensorial form. Now, when I want to describe or understand what these tensors mean, I need to understand the orientation or the coordinate axis that describe the orientation of the atoms. I will not be able to make sense of this tensor or of this tensor independent of understanding these two coordinate systems. So meaning, my description of a tensor is coupled with the corresponding coordinate systems or the frames of reference. It is possible, or our understanding of the tensor, or the way or the destination that we are moving towards, is to express the tensor in such a way that it is independent of the frames of reference. It is independent of the coordinate system. So that is the destination towards which we are progressing. If you consider the sequence of our discussion, we started off by introducing where the tensor is relevant, and then we toned it down and we understood what is Einstein notations and why it is required when we are describing or writing tensor. And now we have we are moving towards the final destination, which is rather the critical feature of the tensor representation. That is, when we express tensor, it needs to be independent of the frames of references that are associated with the system. So that is the goal towards which we are moving. But as things stand now, as we have expressed these two tensors, they are intrinsically coupled with these two frames of references. Now our destination in this lecture is to decouple them, to ensure that when I am expressing a tensor with two different integers associated with it, it is independent of the frames of reference. If I am able to express this, it should be independent of these frames of reference. Now the way we will achieve this destination is, first we'll approach it conceptually or philosophically, try to see how we will be able to achieve it, and then we'll consider the math behind it. So when we talk about achieving or understanding or ensuring that my tensor notation is independent of the frames of reference, what we mean by that is, when we see these indices, the way these are coupled, these indices are coupled to these frames of references, the meaning of these terms stems from this frame of reference. So when I talk about the first term representing the plane or the vector of the plane, this vector, this direction can only be defined in the context of this frame of reference. When I talk about this index representing the direction, this gets a meaning only with respect towards this frame of reference. Now, if I am able to attribute in some way meaning to these indices I, j without referring to the frame of reference here, then I have decoupled the indices of my tensor to that of the frame of reference. So let me repeat, this is rather the philosophy of how we are going to make our tensor independent of frame of reference. So the way we are going to do it is, when I talk about a tensor, it has two indices, and depending on the two indices, the value assumed by my tensor is going to vary. But these two indices themselves, the meaning of these two indices can only be understood when I consider a frame of reference. This is what our understanding is so far. Now, if I am able to define these two indices without ever relating it to the original frame of reference, without ever relating it to this frame of reference here, then I have essentially decoupled my tensor notation from that of the frame of reference. Now, if I am able to bring in meaning to my I and j, meaning to my L and m, without ever associating it to the frame of reference here, then essentially I have decoupled my tensor notation from that of my frames of reference. So what I essentially then have achieved is, I am now able to express my tensor independent of my frame of reference. So this is where the meaning of expressing a tensor independent of the frames of reference comes into play. So what essentially how we are achieving this independence is by rather decoupling the tensor notation from the frame of reference, or to put it another way, by attributing meaning to the indices without the involvement of the frame of reference. If I am able to attribute meaning to the indices without the involvement of, without the conception of the original frame of reference, then essentially I have a tensor expression that is independent of my frame of reference, because I no longer need my frame of reference to describe or to give meaning to my tensor notation. I hope the conceptual foundation is clear, because this is the foundation on which we are going to build our math on. So if this is clear, then even if you don't understand the math, you will be able to appreciate why tensor or how tensor is independent of the frame of reference. So put it simply, tensor has two indices, and what we are going to do is we are going to give meaning to these indices without involving the general frame of reference, right? So that is our goal, and that is how we make a tensor representation independent of the frames of reference. Alright. Now, in order to do that, let us consider a point A, and let us try to describe this point A. So if I want to describe this point A, so any random point A, I want to describe this point A, the only way for me to, or the easy way for me to describe this point A is introduce a frame of reference, a Cartesian frame of reference. So I have my x and y, an orthogonal axis, and based on this orthogonal axis, I will be able to describe my point as A, x, y. So x is the amount of the value that is assumed in the x direction, y is the value assumed in the y direction, and so on and so forth. This is pretty something that we were able to conceive. Now there is also another way for me to represent the point A, of course within this frame of reference xy, using something called like this. So what essentially I have done is, I have started from a point of origin and I have introduced a vector that includes a direction, and the magnitude corresponds to the distance between my origin and the point. So what essentially I have done is, initially I represented my point A using x and y, the coordinates. Now I have taken a second approach. I am representing my point A using a vector that starts from the origin. So this vector has a magnitude and direction. The direction points from my origin to the point of interest, here A, and the magnitude is the distance between the origin and the point of interest. So using this vector now, I am able to introduce or describe my point A. Now this vector is referred to as the position vector. Now of course, this position vector is not a standalone frame of reference. This position vector, the description of this position vector depends on my x's and y. The magnitude, when I talk about the magnitude of my position vector, it needs to come from x and y. And if I want to talk about the origin of my position vector, again it coincides with the origin of my x and y coordinate system. Now of course it is possible for me to rather shift my origin, and now it is, even though I have shifted my origin of my position vector, still within the framework of my x and y coordinates, I will be able to come up with a new position vector which includes, or which now has an altered magnitude and an altered direction, but again the meaning for my position vector comes from basically my x and y coordinate system. Now what we want to do is, again getting back to our original goal, we want to describe the directions we are interested in without involving the frames of reference. So again, if you could recollect, our original goal is we want to describe i's and j's without involving any I vector and j vector that is dependent on my x and y. So one way of describing my I and j would be a vector along the x direction, a vector along the y direction. But we won't want to do that. We want to come up with a way to describe I and j without involving x and y, and that is what we are going towards, and that is the reason why we started off with this point A. Again, our interest is, we have an interesting direction. We have a direction that we are interested in, that is I direction and the j direction. These are the directions that we are interested in. We want to describe this direction without the involvement of x and y. That is our goal. So if I am able to describe these indices, these directions like I and j without the involvement of x and y, then I have decoupled the direction of my interest from the frames of reference. I hope that point is clear. I am decoupling the direction of my interest from my frames of reference. Now as it stands, the way I will describe my I vector, the I unit vector is the direction that is along my x-axis. The j vector would be the direction that is along my y-axis. But now I have to come up with a way that is independent of my x and y. So that is our goal. If I am able to come up with a way, then I have decoupled my I and j from x and y, meaning my I and j are independent of my x and y. Amazing. Now in order to do that, I introduce another point that is close to my original point, but in the direction that I am interested in. I want to decouple my i's and j's from x and y. In order to do that, I am introducing another point in the direction that I am interested in and close to my original point. So when I do that, I end up with a prime. Again, I am not involving any x and y here. All I am doing is I am introducing an a prime, and this a prime is along the direction of my interest and it is close to my original point. Now from the same point of origin, I'm introducing a position vector to describe this new point a prime. So I have an original point a prime and I'm introducing a new point, or I have an original point a, I'm introducing a new point a prime. Only the reason I introduced this a prime in a specific spot is because there are two criteria that needs to be fulfilled. One is it needs to be close to a, and it needs to be along the direction that I am interested in. So once I have introduced the point a prime, then I am introducing a position vector from the same point of origin of r to describe its position. So I have r prime that describes the position of the newly introduced point a prime. Now when I consider the difference between r prime and r, I end up having a new vector called e1. So all that I am doing is I am considering the difference between my r prime and r, and the new vector that points in this direction is e1. Now if you want to verify how e1 points in that direction, or what is the foundational math behind it, so this you can see here. You can try to add your e prime, assume the existence of the a prime, e1 rather a priori, and then you will be able to say how the difference between R prime and R is E1. So this is just the proof of how the difference between these two is E1. So essentially now what we have is, we have a vector E1 that is nothing but the difference between R prime and R, and it is pointing in the direction that we are interested in. So E1, I'm able to describe it independent of my x's and y's, but based on my R prime and R. So the difference between R prime and R is now giving me a vector E1. Now what I can do is, this E1 can be of any distance, but I want to have a unit vector along that direction. So therefore, I divide it by the magnitude of my E1. So I have 2 points A and A prime. I've considered the distance between these 2 points. I've been able to calculate the distance between the 2 points A and A prime by considering their corresponding position vectors. Now I want to estimate or translate this E1 vector into a unit vector, so I'm dividing it by its magnitude. So when I divide this by its magnitude, what I will end up with is a unit vector that is pointing in the x direction. So when I divide my E1 with its magnitude, all the magnitude goes away, it cancels out, it becomes 1, but the direction remains the same, and this direction is parallel to my x-axis, which is nothing but my I hat, or the vector I that describes the basis vector I that describes the direction of x-axis. Now what essentially I have done is, I have now been able to bring up a unit vector I using two position vectors. Now of course, when I use these two position vectors, when I describe these two position vectors, I used x and y coordinate system to describe them. But even if I change my x and y coordinate system with any coordinate system, still I will be able to recover a unit vector along a direction that I am interested in. Even if I replace my x's and y's, even if I describe my position vectors r's and r prime here, even if I describe my position vector r and r prime, from using which I'm calculating my E1 and which ultimately translates to my I, even if I describe this using L and M, using any coordinate system, still I will be able to recover a unit vector along my desired direction. So that means I am now able to introduce or give a meaning to I, which is my desired direction, without the dependence of my coordinate system. Let me repeat, what essentially we have done is, we have found a way to represent or describe the unit vector I using two different position vectors. Even though originally these position vectors were defined by x and y, I can consider any frames of reference. It could be x prime or y prime, it could be L and M, any different frames of reference I could consider, but irrespective of the frame of reference I consider, because of the operations that I have performed. My unit vector depends on the difference between the position vector and the magnitude of it. My unit vector just depends on the difference between the position vector and the magnitude of it. I could consider any number of frames of reference. My unit vector, the way I'm defining my unit vector, just depends on the difference in the position vectors and the magnitude of it. So if I'm able to express my unit vector using the position vector, that could be dependent on any frame of reference. So essentially the description of my unit vector is no longer based on the frame of reference, it is based on my position vectors, and these position vectors can be dependent on n number of frames of reference. So as the frames of reference, even if the frames of references change, I will be able to come up with positions vector that can, using which I will be able, I can describe my own unit vectors. Now the same thing I could do for the other point. So there is another direction that I am interested in. So I am now able to bring a meaning to my I. I can also bring a meaning to my j using the same position vector. So all I have to consider is another point close to my original point, but in the direction that I am interested in. So I have my a double prime here. So once I have my a double prime point, I can then subsequently introduce a position vector that describes my a double point. So my origin now has moved away from the origin of my x and y. Now of course I can use any ways to describe my r double prime, but again the approach remains the same. If I want to describe the vector that separates my a and a double prime, all I have to do is take the difference between r double prime and r, and if I do that, I end up introducing a vector called E2. And when I divide it by the magnitude of E2, I end up having a unit vector pointing at a direction that I'm interested in. So that is exactly what we achieve. So ultimately, we have now arrived at a way to describe the unit vectors I and j without involving x and y. The original description was I is a unit vector that points along the x-axis. J is a unit vector that points along the y-axis. Now, I and j are the unit vectors that we have built by using position vectors. Now, the position vectors, irrespective of how you define your frames of reference, you will be able to achieve the same expression for I and j using the position vectors. So ultimately, since R can be, the position vector can be described in any frame of reference, and my description for I and j comes from R, my description for I and j can be brought up from any frame of reference. So ultimately, this description of I and j is rather independent of the frames of reference. So basically, when I see an entity I, j, so let's say, let's go back to our original epsilon ij. It needs a direction, a vector that describes a plane. It needs a vector that describes a direction. I can safely say that these i's and j's can be represented using the position vector. It does not need any specific frames of reference. It can be described using the position vector, and this position vector works for any different frames of reference that you use. So all that you need is to choose the direction that you are interested in, and in that direction you will be able to build your unit vector, irrespective of what frames of reference that we consider. So the way we have decoupled the tensor notation from that of the frame of references, we have now given meaning to the indices through the position vectors, and these position vectors, the role the position vector play is going to remain the same independent of your frames of reference. So because you have defined your unit vectors based on the position vectors, and these position vectors are going to play a role, the same role independent of the frame of reference, the expression, the overall expression for the tensor is rather independent of the frames of reference. So the way you get rid of the influence of frame of reference, the need for introducing the frame of reference while you are expressing things in tensor notation, is by expressing or giving meaning to these notation through the position vectors, and the role played by the position vectors is rather independent of the frames of reference that you choose. Now, of course, there are other mathematically less rigorous ways of expressing your strain independent of the frame of reference. So we also refer to this as von Mises strain and von Mises stress. So there is something called as von Mises stress. So what essentially von Mises stress does is it considers all the different elements of the stress, the tensor representation of the stress, and then it translates it into a scalar value, and so that scalar value, of course, is going to be independent of the frame of reference. So it's a scalar, so it's ultimately going to be independent of the frame of reference. So it's called basically the von Mises stress. Basically, it involves something called as a J2 invariant. The term J2 invariant is it is independent of the frame of reference. So using J2 invariant, you will be able to calculate von Mises stress. So it's a scalar, and the von Mises stress, it's not exactly a scalar, but still largely it's a scalar, meaning it is, because of its scalar nature, it is independent of the frames of reference. Now, of course, you can use the well-known eigenvalues and eigendirections or eigenvectors in order to rather reduce the, or in order to ensure that all these tensors are involved, or they are expressed with respect to a single frame of reference. So you can consider all the different frames of references, and then within a system, and you can express them using a single frame of reference. So these are other alternate ways of expressing your tensor, but one rather implicit way wherein we are able to decouple the effect or the role of frame of reference in the tensor notation is giving meaning to these indices I and j, not based on the frames of reference, but based on the position vectors. So if and when we are able to give meaning to these i's and j's and other indices of the tensor using this approach here, then we are essentially decoupling the role of frames of reference in the description of our tensor. So then when I see that there is a tensor notation, let's say represented in this way, and it is said that this tensor notation is independent of the frame of reference, then what it essentially means is these values get their meaning not from the frame of reference but their position vectors are. And depending on, so I will be able to come up with a meaning to I and j by varying this, by considering the different position vector along the direction that I am interested in. So we have now understood, at least conceptually, how we are decoupling the role or these coupling of frames of reference to that of the tensor. We have decoupled it by describing these indices using a different approach that involves position vector. So with this we will wind up this session, and we will rather consider the application of the tensor notation again back into the material behavior in the subsequent lecture. Goodbye guys.